Good afternoon, everybody. My name is Paritt. I'm working as a research fellow at the Spinal Cord Injury Research Facility at the Center for Brain Research, University of Auckland. Today, I would like to present my research topic. It's about microfluidic gradient generator to study the axon injury and regeneration. Let me start by showing you the interesting stat. New Zealand has the highest incidence rate of spinal cord injury in the Western world. Every year we have about 80 to 130 new cases per year, and the majority causes of the spinal cord injury is accidents, falls, and sport injuries. And the average cost of care is about 200,000 New Zealand dollars per year. This is a big impact on not only New Zealand but also have a global impact as well. So what we are doing now, we build the bridge connecting between the clinical and research team. In terms of clinical practice, spinal cord injury is a damage of spinal cord tissue due to the mechanical injuries. But in terms of cellular level, the axonal injury is the most common feature of spinal cord injury and is the key of research interest. We are developing the new system that we can provide the culturing the neurons, and we can create the damage to the axon in order to unlock the secret of how to reconnect the axon again. So my aim of research is to develop the concentration gradient generator for axon guidance by chemotexus using microfluidic system. Let me explain with this diagram. We create a new system, like we call neuron on a chip. It's culture the neuron inside. Thanks for the system that can create the gradient concentration for the active reagent, like nerve growth factor, from point A to point B, and allow the axon outgrowth toward the direction and space as we want. Start with the material. We use the advanced microfabrication to produce neuron on the chip at the side of the glass-like. And the special design having the chambers, each chamber connecting each other with a micro channel is very tiny with a 5 micron thickness. This system allows the neuron culture and provide an axon outgrowth to the micro channel. And then we create the gradient concentration of the fluorescein dye that is shown in the picture with the green color from the lower concentration, point A, to the higher concentration, point B. We combine the system sizing pump with the microfluidic fluorescein microscope and image processing to quantify the amount of fluorescein concentration. Let's see the result. The diffusion of fluorescein molecule can be generated along the microchannel, and we use the image processing to quantify the amount of fluorescein molecule from intensity to concentration as shown in this graph. Controlling the different flow rate from 1 to 10 microliter per hour can change the gradient profile. For example, the concentration gradient increasing every 2 or 3 to 1.2 nanogram per mil at each step of this type of microns. And this system can provide the gradient establishment easily within 2 hours, and we maintain the same gradient and concentration for the long-term culture for neurons from day 1 to day 5. But however, after day 7, the gradient profile was dropped significantly due to the evaporation. But for 5 days, for culture is more enough to make sure that axon can generate within the 2 millimeter and enough for study. The system provides us many advantages. For example, it's very easy to set up, inexpensive, provide fast gradient generation, as well as reduce the amount of reagent consumption. This part of my project is our ongoing project, In the future, we're going to culture the neurons from the rat embryos, and we're going to study the axon injury and regeneration. We're going to combine the microelectrode arrays to record the electrical activities of the single neurons. And my big team working on the bioelectronics implant with control drug delivery. On the bottom, on the right corner image, we're showing our prototype flexible microelectrodes with control drug release system that we will use in animal model. In the future, we're going to implement in the clinical study of the spinal cord injury and rehabilitation. Let me summarize my study. Microfluidic culturing devices combining with gradient generator have been developed at University of Auckland. The long-term stable gradient profile with dynamic control of flow rate is achieved through the design of microfluidic system. Further investigation and study will continue for ongoing collaboration between the clinical and biomedical research. Luckily, we have a good relationship with the Auckland Spinal Rehabilitation Unit that is part of the Manukami's help. I would like to say thanks to my supervisors and my colleagues team at the Spinal Cord Injury Research Facility and School of Pharmacy at University of Auckland, and also the Ko Awatia to allow me to present my study. Thank you very much.